Hello, everyone. Welcome to our presentation. It is so great to be here. I am Maria Vik. I'm a lead pipeline programmer in the MetaHuman team, and I work on creation of MetaHuman characters database. I also support our clients and help them to adopt MetaHumans in their projects. Here with me is my colleague, Nemanja Krža, senior pipeline programmer who also works in the MetaHuman pipeline team. Today, we're going to help you to better understand MetaHuman rigs and technology behind it. What are we going to cover today? Firstly, we are going to give a brief overview of MetaHuman ecosystem and MetaHuman asset. Then we are going to deep dive into MetaHuman rig, its components, and technology behind it. Next section would cover how the MetaHuman rig evolved over years. And lastly, we will give you some useful tips and share several links so you can go and explore further. Okay, let's start with MetaHuman product overview. MetaHuman is a complete framework that gives everyone the power to create and animate highly realistic human characters for any Unreal Engine project. You can create, animate, and calibrate your MetaHuman using tools from our framework. First step is creation. MetaHuman Creator allows you to quickly create photorealistic digital humans, fully rigged and ready to use. You can create MetaHumans in minutes, starting from one of the preset characters, or convert your own custom mesh into a MetaHuman using the plugin for Unreal Engine called Mesh to MetaHuman. Next step is animation. With MetaHuman Animator, you can reproduce facial performances as high-fidelity animation on any MetaHuman. Every expression and emotion is accurately captured and replicated on your digital human. It is simple and straightforward to achieve incredible results. Then comes calibration. You can change how MetaHuman looks by using a set of libraries called DNA calibration. Okay, MetaHuman is not a single asset, but a collection of assets and their dependencies. Main components would be face or head rig, body rig, groom, and clothing. When downloading MetaHuman from Quixel Bridge, user can choose to download UAsset, source asset, or both UAsset and source asset. Source asset contains MetaHuman DNA file, which we will explain in detail later. When downloading for Maya, this asset also contains body rig scene and combined scene where you have both head and body. The main parts of UAsset are head and body. Head contains skeleton, skeletal mesh, control rig, any blueprints, materials and textures, and physics asset. Groom is also part of the head and contains groom asset, static meshes, binding asset, materials, and textures. Body has pretty much a similar set of components as the head. And for the clothing, the main parts are skeletal mesh, materials, and textures, and also it has a physics asset. Before we go to the main part of our presentation, which is facial rig, I'll take a couple of minutes to talk about other components. Let's start with grooming. As you probably know, grooms are an integral part of MetaHumans and do provide an extra level of realism to digital characters. However, the strand-based rendering can be quite expensive and has a large impact on performance. As you can see, strand-based grooms are available for LOD 0 and 1, but also for those LODs, we have card-based grooms, so user can choose here. Cards are available for LOD 2, 3, and 4, and you can see how quality deteriorates when going to lower LODs. And for LODs 5, 6, and 7, we replaced cards with helmets, as you can see here. Here we can see a detailed overview of groom assets per LOD. Hair, mustache, and beard do have the same setup. just a few notes. In case of the short hair, one way to optimize it for LODs 5, 6, and 7, hair will be baked in texture as there is no need for the helmet. For ultra-short hairstyles, you can choose between strands and texture even for LOD 0 and 1. For other LODs, of course, we have only textures available. On average, LOD 0 hair will have somewhere between 50 and 100,000 curves. The same hair would be around 40,000 triangles. So the size of LOD 1 groom asset will be 70% of LOD 0. On average, every lower LOD will have around 50% the size of its predecessor. Regarding simulation, physics will be present on LOD 0, 1, and 2 for long hair only. In Unreal Engine 5.4, the continuous LOD feature for strands allows for a more efficient rendering of hair in real-time environments. The Auto LOD option automates the process of adjusting the complexity of these strands based on the camera's distance from them. This means that as the camera goes closer or further away, the detail level of the strands adjusts dynamically without any noticeable changes or performance drops. This seamless transition ensures that players experience a consistent visual quality while also optimizing the game's performance by reducing the rendering load when high detail is not necessary. On the other hand, a manual option gives developers direct control over when those LODs changes occur, which can result in visible shifts of LODs. Let's move to clothing. Garments follow our body rig, and we have 4 LODs. In total, our team has designed 4 tops, 7 bottoms, and 7 shoe styles to choose from. For every garment, we need to produce 72 versions of the asset. This is because we have 4 LODs and also 18 body types. In this table, you can see how many vertices we have for every mesh per LOD. As you can see, the actual number of vertices may vary significantly. And now, my colleague Nemanja will talk more about MetaHuman Rig. The stage is yours.
Thank you, Maria. Hi, everyone. It's great to be here. To better understand the MetaHuman Rig, our first stop is the MetaHuman DNA file. Let's talk about how the format came to be. Our first rig was created in 2006 in Maya, and it used SDKs. They were used to drive joint animations and blend shape activations. In time, corrective expressions were added, originally for expression combinations affecting the eyes, later expanding to other regions of the face. As the number of expressions grew, both primary and correctives, we implemented ways for our artists to model shapes more efficiently. This, in turn, led to further increases in the number of expressions. As time went by and our rigs evolved, we noticed degradation in performance, and that led to experimentation with different solutions. One of those solutions was generating XML files which contained descriptions of the SDKs that drove joint animations and blend shapes. Another was generating code, C++ or C#, for example, with clients running it in Engine, or building Maya plugins which improved performance in Maya. Finally, we found out that the optimal solution for us was the precursor to the MetaHuman DNA, a proprietary binary file format which can be used to evaluate rigs. This enabled some of our most well-known demos, such as Siren at GDC 2018 or Andy Serkis performing Lies from Macbeth. Further research and improvement driven by our service work brought us to where we are today, and that is the metahuman DNA. A metahuman DNA is organized in layers, with most layers depending on one of the previous ones to make sense of the data. We start with the descriptor. It contains information about the character that the metahuman DNA file is representing, with additional metadata. That metadata can be used to give more context to data found in other layers. Next comes the definition layer. It can tell us more about the elements of the rig and how those elements are divided into LODs. Geometry and behavior come next. Geometry contains data about mesh points, skinning, and corrective blend shapes. Finally, behavior is what makes a character unique. As the name suggests, it describes how our metahuman behaves when animated. So let's dive deeper into the specifics of each layer and also look at some code examples to start extracting data. So to start, we need a metahuman DNA file, which is a part of the source asset, as Maria mentioned. This example and many more can be found in our metahuman DNA calibration repository. So if anyone used the source code found there, this should be pretty familiar. While examples found in that repo focus more on assembling, modifying, and exporting metahuman DNAs from Maya, the following examples will focus more on the structure of the DNA file and the data present in its layer, so it won't require Maya to run them. So for the descriptor, we can find metadata about our characters, so its name, the number of LODs, the units in which all our translation and rotation values are written in. We can also read any miscellaneous data present, and more importantly, the name of the database that this particular character belongs to. This will be important in a minute. The definition layer contains data about the controls, their number, their names, both for phaseboard or GUI and raw controls. So the names of joints, their hierarchy, and which joint each LOD is a part of. The number of meshes and their names and how they are divided into LODs. Similar information can be found for blend shapes and animated maps. And finally, the bind pose is a part of the definition layer as well. As the name suggests, geometry contains information about 3D points contained in a rig. We can extract data about topology and vertex positions, for example, and also the values of corrective blend shapes relative to those points. Other than that, skinning data is present in this layer, allowing us to query information about the maximum number of influences per vertex and the actual values of weights for each vertex of every mesh. Now we come to what makes a metahuman unique, and that is the behavior layer. We can split data stored in this layer into two sections, inputs and outputs. I'll focus more on the outputs here. So for inputs, here we have information about how we can map values of GUI controls to values of raw controls. And also, according to raw control activation, a certain number of corrective expressions can be activated, and the rules how they are activated are stored in this layer as well. On the output side, we can divide the section further into three groups, so joints, blend shapes, and animated maps. I'll focus more on the joints here. So for joints, their animation for every joint attribute, meaning translation, rotation, and scale, is stored in this layer. Joint attribute values are stored only for expressions which affect them. For example, we won't store the jaw joint animation for expressions affecting the brows. This allows us to reduce the file size of the metahuman DNA. The data for joints is stored in joint groups. These groups contain non-intersecting sets of joints. the union of which equals all joints present in our metahuman DNA. How different LODs affect the joint animations is also contained in these joint groups. So for blend shapes and animated maps, we store their activation and also how LODs affect their activations. Let's move on to some simple code examples where we can actually start combining data found in different layers into other useful information. One example of using data found in the definition layer is to extract the joint hierarchy. I'm going to pause for a couple of seconds so everyone can get a chance to read this. So in this example, I'm using a pattern which is going to be repeated in all other examples. You can extract the names of elements of the DNA file by iterating over count and then grabbing the name for each index. That is what I use to find the index of the facial C jaw joint. And then I can use the getJointParentIndex method to get the index of its parent joint and then finally get its name. You can use this code snippet to extract maybe pairs of parent-child joint names, if that's what you need. What about blend shapes? Not all blend shapes are present on all meshes, and we can extract that information from the DNA file. Again, I'm going to pause here for a few seconds. In this example, I wanted to find out which blend shapes exist on the teeth LOD0 mesh. I used the same pattern as in the example on the previous slide to find its index. And to actually get the information I need to iterate over the mesh blend shape channel mapping data. This data contains pairs of indices, the first one representing the mesh and the second one representing the blend shape. So I can just compare the mesh index of the mapping data with my wanted mesh index, and if they match, I can record the channel index. Moving on to data found in the behavior layer, let's calculate joint animations when controls are activated at their maximum value, and let's also specify the active LOD. So I'm going to give everyone an hour to read this, and no, there is a better way to do this, and it's rig logic. So what is rig logic? Rig logic is a runtime facial rig evaluation solver system. But what does that mean for a metahuman? It's a transformation of several arrays of float values. First, it transforms an array of 174 float values into an array of 269 float values, which is then transformed into an array of 8,694 values. So everything's clear, right? Yeah. But what do these numbers represent, actually? Our first array represents the values of GUI controls. The next array represents values of raw controls. Rig logic allows the user to provide either the GUI controls, and then it can transform those into raw controls, or the user can provide raw controls explicitly, thus removing the need to have the first transformation mentioned in the previous slide. And finally, using raw control values and the data found in the behavior layer, rig logic calculates the actual output values for our rig. So 7,830 joint attributes, meaning translation, rotation, and scale for all of our 870 joints per the 3 axes, 782 blend shape activations, and 82 animated map curves. To do this, rig logic just needs a metahuman DNA containing the behavior layer, which implicitly requires the descriptor and the definition layers, as I mentioned before. So besides the performative evaluation of a metahuman rig, rig logic has a few other benefits. So one of them would be that the same animation can be applied on any LOD for any metahuman. Another one would be runtime adjustment of animation in engine. For example, an NPC's eye gaze could be following the player character during dialogue. So let's go back to our example of calculating joint animations. Now, using rig logic, this becomes trivial. The only thing we need to do is to set the control values and our target LOD, calculate, and then read the joint values. While being much more concise, it allows the user to focus on higher level concepts, such as controls, instead of specific joint attribute values, and is also much more performant. Now that we know what metahuman rigs are made of and how they're evaluated, Maria will explain how they and the metahuman product suite evolved over the years. Take it away.
Thanks. Thank you. So MetaHuman as a product had several significant milestones that I want to mention now. Of course, 2021 was the most important year as MetaHuman Creator was launched then. In 2022, we released Mesh to MetaHuman plugin and shared our core libraries, DNA and DNA calibration. 2023 brought us MetaHuman Animator and also an interesting demo at GDC when we showcased ML Body Deformer rig. This year at GDC, we announced MetaHuman coming to UEFN. Now I'm going to focus on face rig and give you some interesting numbers. Let's see them. When we think about geometry, here you can see how many vertices each mesh has per LOD. You can also notice that not all meshes are present in each LOD. LOD 7, for instance, has only head, teeth, right and the left eye meshes. Of course, the head mesh is the heaviest, with 24K vertices. It is followed by teeth with 4K and eyelashes with 2K. However, when we move to LOD 1, you can see that geometry is reduced by half for the head mesh. Moving down to LOD 7, we end up with only 211 vertices in total, if my math is correct. Here you can see some other rig elements. For instance, blend shapes are only present at LOD 0, and we have 782 of them, with some existing on multiple meshes. Nemanja already mentioned that. In the table on the right, you see how many of them each mesh has. Of course, head mesh has the majority of 737, while some meshes do not have them at all. Moving to joints, you can see how many of those are in the skin cluster per LOD, and for LOD 0, in the table on the right, you see how many influences each vertex maximally could have. Head and cartilage have 12. Animated maps are activated only for LOD 0 and LOD 1. Observing lower LODs, here you see what is the influence per vertex for every mesh. I do hope this could be useful when you have some specific requirements and for your targeted platforms and want to choose wisely. Moving to body rig. Body rig is not as complex as head, as you can see from this table. Across 4 LODs, geometry goes from 30K to 1K. In the skin cluster, we have 320 joints for LOD 0 and only 38 joints for LOD 3. Regarding influence per vertex, it is mostly 8, 4 only for LOD 3. We use RBF, radial basis function, as a corrective deformation system, with solvers which have predefined poses, allowing us smooth interpolation between complex deformations. It is like an extra layer of refinement on top of primary rig joints. RBF poses are only defined for LOD 0 and 1. We have 44 solvers which contain 132 different poses. Each head LOD is not universally compatible with every body LOD. In order to have this compatibility, we need to match neck seam vertices on both meshes. Here you can see what combinations work. For instance, body LOD 0 pairs with head LOD 0 and 1, whereas body LOD 2 is compatible with head LODs 4 and 5. Now I'll briefly discuss the versions of MetaHuman Creator. Generally, MetaHuman Creator versions align with Unreal Engine updates. We initially launched MetaHuman Creator version 0.5 for UE 4.27. Then we updated to version 1.0 and released it for UE 5.0. You can observe the progression of our versions and their compatibility with different UE versions. During this period, our rig was also evolving, and I will explain why. Although MetaHuman Creator undertakes 5 different major versions, rig evolution is somewhat slower, and we had 2 updates in the last 3 years. Not long after we launched MetaHuman Creator, we got the feedback regarding neck fidelity and how neck expressions do not always look great. The first update of the rig itself came in UE 5.0. We removed some joints from the rig specification. I'll explain what exactly in a minute. Then, while preparing for the release for UE 5.2, we got a feedback from the team who worked on MetaHuman Animator that there is a problem with animation curves and we should consider improving tongue-related expressions. So we changed the volume of the tongue and actually added several tongue expressions. Additionally, we added RBF setup for the neck to get even better fidelity. At that point, we put in use one metadata found in a MetaHuman DNA file called dbName, and decided to use that to track rig specification changes. If you execute the command get dbName, you will now get the value mh.4. Previously, it would return dhi as a value. Obviously, the rig is not the same in UE versions 4.27 and 5.0, so I put an asterisk to make distinction between them. Now I'm going to give a detailed overview of rig updates between versions. First, I'll compare rigs between engine versions 4.27 and 5.0. As I have said, the neck expressions were reported as problematic ones, so our rigging team tried to fix it by removing and adding some joints. For LOD 0, 22 joints are removed, which resulted in fewer joints in the skin cluster. However, for lower LODs, we actually included more joints. As you can see, for LOD 7, the number of joints did not change, but we actually had one replacement. The second rig specification update between UE 5.0 and 5.2 actually got more updates. We added some tongue joints, and I listed them all in this slide. Next important update was the list of the row controls. We removed 4, but added 15 for tongue-related expressions. And as I already said, This was important for MetaHuman Animator. Since raw controls are changed, we also changed GUI controls, which you can see in the facial GUI board. Just pay attention to the tongue section and tweakers. I do hope you saw the difference. In this slide, you can see a comparison between those versions in the number of blend shapes on LOD0. The number of blend shapes increased because of added expressions on both head and teeth meshes. In the table on the right, you see how many raw and GUI controls were added. We covered a lot of information today, so let's wrap things up. The key takeaways would be MetaHumans are evolving and will continue to evolve. We do try our best to gather feedback from our users and to try and push our limits.
You don't need to remember any numbers we showed earlier. Everything is written in the MetaHuman DNA file and can be easily read from there.
And now some useful links, so you can deep dive even further. DNA lib, which we used for all our code snippets, today you can find on GitHub in DNA calibration repository.
The white paper on rig logic and its core ideas can be found on this link. Understanding what rig logic does is not mandatory, but will allow you to have a higher level of understanding of what MetaHuman rig evaluation is.
And finally, DNA calibration functionality and how you can customize your MetaHuman was the topic of my talk last year at Unreal Fest, so you can check it out. Thank you all for coming. Now we can have some questions.
Yep.